all of the op-amp circuits we have looked at so far have had negative feedback. In other words, something, whether a resistor or a capacitor or possibly something else, was connected from the output of the op-amp back to the inverting input. With this being true, we made a fundamental assumption that if it was within the power of the op-amp to do so, it would make the voltage at the inverting input equal to the voltage at the non-inverting input, and this made our analysis of the circuits quite a bit simpler actually. But now we have to look at circuits where this is not true. There is not negative feedback. To sort of set this up, let's look at the basic non-inverting amplifier, and we're going to assume that the operational amplifier is running on plus and minus 15 volts and that it has rail-to-rail outputs. In other words, the output of the op-amp can actually go right up to the power supply limits of plus and minus 15 volts. In addition, we're going to assume that the input bias currents are 0 and that the open loop gain of the op-amp is actually infinite. Now, you cannot obtain an op-amp with infinite open loop gain or 0 bias currents, although you can get ones with very high gain and very low bias current. You can, however, get operational amplifiers with rail-to-rail outputs. They typically cost a bit more, but they are available. Let's begin by looking at the I/O characteristic curve of this simple amplifier, and we're going to start with a gain of 1. For a non-inverting amplifier with a gain of 1, the feedback resistance is 0. In other words, it's just a wire, or in other words, that's a voltage follower. As you increase the feedback resistance, the gain is going to go up. But first, let's look at the characteristic curve for a gain of 1 and talk about that briefly. Note that as long as the input is between plus and minus 15 volts, the output is exactly the same thing. It's just a linear progression. When the input's minus 15 volts, the output is minus 15. When the input is plus 2, the output is plus 2, and so forth and so on. Now, what happens if the input goes outside of that range? If the input, for example, goes to 17 volts, the op-amp can't do that because the highest it can go is 15 volts, and so it is now in what is called the saturation region. It's gone as far as it can go. It can't go any farther, and actually at this point the negative feedback breaks down, and the op-amp will not be able to maintain the two inputs at the same voltage. And the same thing happens on the negative end. If you go more negative than minus 15, then the output's going to pin itself at minus 15 volts. It can't go past that. If you increase the gain, in other words, if you increase the feedback resistance from a simple wire to some actual positive resistance, the gain's going to go up. But now what that means, if you were to go to a gain of 2, then the op-amp can still only output a maximum of plus and minus 15 volts. So if you had a gain of 2, then the limits of your input without saturating the outputs at plus and minus 15 would be plus and minus 7.5 volts. If you had minus 7.5 volts times 2 is minus 15. If the input went more negative than that, you can't go past minus 15. So basically what's going to happen as you increase the gain, the diagonal line is going to become more and more vertical, and the space between the points where it saturates get closer and closer. So let's run a little simulation of this, and we're going to increase the gain from 1 to 100. Here we go. And as you approach 100, note that at a gain of 100, then the maximum magnitude of the input voltage is going to be 0.15 volts, because 0.15 times 100 is 15. And so if your input voltage goes more negative than minus 0.15 or greater than plus 0.15, then the op-amp's going to saturate. So you've got a really narrow window there of usable input voltages to amplify with a gain of 100. We can do the same thing and run the gain of this one up. Let's again increase the gain from 100 by a factor of 100 up to 10,000. So here I have expanded the horizontal axis so that now you see that it looks just like the original one with a gain of 1 except for the horizontal axis. Note that those saturation points are now at minus 0.15 and plus 0.15 volts. And again, if we increase the gain, that linear region between the two extremes, plus and minus 0.15 volts, is going to narrow and get closer and closer and closer. And eventually, it's going to get down to 1.5 millivolts, because 1.5 millivolts times 10,000 is 15. So if you have a gain of 10,000, here we go. The maximum range of input values that will not saturate the outputs is plus and minus 1.5 millivolts. Let's do this one more time just to show that it will continue forever and ever, basically. All right, here's our picture with a gain of 10,000. Now note over in the bottom right corner it says times 10 to the minus third. So plus and minus 1.5 millivolts is your range of really usable input voltages for it to be in the linear region. And if we run that up by a factor of 100 to 1,000,000, it does exactly the same thing it did before, except for the usable range of input values. Now your usable input range is plus and minus 15 microvolts. Now, if we did this again, it would just keep going like this, and next you'd have 150 nanovolts, and then you'd have 1.5 nanovolts each time you went up by a factor of 100. If you were to continue this until the gain approached infinity, now that means that that feedback resistor approaches infinity, or you just pull it out altogether. There is no feedback resistor. There's where our no negative feedback comes in. You simply get rid of that feedback resistor. But as the gain approaches infinity, the distance between the 2 points where it saturates on the positive and negative sides, the distance between those approaches 0 also. In other words, that transition between the negative saturation point and the positive saturation point becomes essentially instantaneous. So for any negative voltages, it pins itself to the negative supply. For any positive voltages, it pins itself to the positive supply. So now basically what you've got is you've got a device that effectively outputs the sign of the input. If it's negative, the output's negative. If the input is positive, the output is positive. This is your basic comparator. Effectively, it compares the input to ground, because now note, with the feedback resistor gone, you've just got a resistor to ground on the inverting input, and since we're assuming the bias currents are 0, that resistor really serves no purpose, so we could just throw it away and connect the inverting input directly to ground. And so what the op-amp looks at is the difference between Vn, which is connected directly to the positive input, and V minus, which is ground. So if that difference is negative, in other words, Vn is negative, the output pins itself to the negative supply, and vice versa. Now this is the simplest form of the comparator. We're going to look at quite a few variants of this in the next video.